All right, well, welcome back to your favorite Math 126 course. We're taking a look at graphing polynomial functions. Last time we talked about the characteristics of polynomials, such as how many terms that they may have. So they'll have up to n minus 1 turns. And then we talked about end behavior, and we talked about zeros and their multiplicity. So we'll revisit quite a few of those concepts today. Let's take a look at this first example here. For this function, it's already in factored form. Let's talk about the zero. So here's our function. If I was finding my x-intercept, we'd let y be 0, and we'd solve. And if you notice, for this one, I just have one factor, x equals 0, set the next factor equals 0, and set the last factor equal to 0 by the zero product property. And I solve each of those. So it looks like our first 0 is 0. And there's only one of those factors. So it's going to cross through there, right? So the graph will cross through, either increasing there or decreasing there. So one of those two ways. The next one is x equals 5. Again, there's only one of those factors, so it'll cross through there as well. 1, 2, 3, 4, 5. So it's going to cross through one of those two ways there. And then the next one is negative 3. Multiplicity is only one of those, so it'll cross through there as well. Either increase through there or decrease through that negative 3. And then the graph behaves like, now remember, this is our function. It's not in standard form, so I'm going to go ahead and multiply this out. Put in standard form, plus 3x minus 5x minus 15. So it looks like we have x times x squared minus 2x minus 15. Multiply the x through. So it behaves like this first term, x cubed, for large values of x. In other words, as x increases or decreases in magnitude. So in other words, we're thinking about the end behavior of the degree of this. Well, the degree is odd. It's odd degree. N is odd. So then we say, well, does it behave like x cubed with a sub n being positive? Or when n is odd, is the leading coefficient negative, which would mean it would go down up to the left and down to the right. Well, the leading coefficient, the number in front of the x cubed, is 1. It's positive. So we're this scenario. So I know this eventually goes down to the left and up to the right. And the other thing I want to think about, because it's asking us to find the zeros, the multiplicities, the turning points of this as well, since it's an x to the third power. Whoops. So we'll have at most n minus 1 turning points, since it's a third degree. So 3 minus 1, at most 2 turning points. Okay, so what you'll see is, since it goes down to the left, up to the right, it's going to come up, it's going to cross through here, it's going to have to come down, cross through here, and then it'll eventually come back up through there. Now the accuracy of this would have to be based on some points. So ideally, I'm going to also sketch some points on this as well. That's how I'm going to find some other values. So I could throw in something to the left of negative 3, like negative 4. I already know negative 3 hits 0. And then I'd throw in like negative 2, negative 1. 0 already hits 0. I'd also throw in like 1, 2, 3, 4. We already know 5, it hits 0, and maybe 6. Right, so I'd throw a bunch of points in and kind of see where those hits, see where those values are, and then I could make my graph a little more accurate, right? So let's throw in -4. Oops, here's our function. Let's throw -4 in. So it looks like I got -36. So -4 is like way down there, -36. So this shoots down a lot quicker. So it's got to hit -36. If I throw in -2, I'd have -2 times -2 minus 5, -7, -2 plus 3, 1. So it looks like this would be 42, right? So clear up there at, oh, I'm sorry, that's +1. I did that wrong. -2 plus 3 is a 1. There we go. It's 14. -2 comma 14. Well, that's still way up there. So it's going to have to go up, hit that -2 comma 14. Throw in -1. I'd have, let's see what -1 would give us here. Erase this. So I'd have -1, -1 minus 5, -1 plus 3. So -1 gives us 12. So then it hits -1, 12. So it comes back down, hits -1, 12. Again, I can't reach this on this graph, so unless I make it go by 2s or whatever, but I don't want to. So I'm going to hit this 0. Then throw in like 1, 2, 3, 4, 5, and so on. But anyways, you'll see this like go way down. I'm not too worried about the points at this point. I just kind of want you to get a feel for what this graph looks like. All right, here's our next function. Y equals 2x minus 3 squared, x plus 4 squared. We're going to find our x-intercepts. So notice we have 2 of these x minus 3s, 2 of these x plus 4s. So you set each of those factors equals 0. And you notice x equals 3, but there's 2 of those x equals 3. So you say with multiplicity of 2. So the first 0 is 3, and there's 2 of them, 2 of those factors, x minus 3, x minus 3. So with multiplicity 2, that means it touches because there's an even amount of them. 1, 2, 3. So I hit here. So I'm either going to touch it like that from the top, or the graph will just touch it from the bottom. Now let's do the next one. X plus 4 equals 0. So x equals -4. There's 2 of those. So with multiplicity of 2. So there's a 0 of -4. There's 2 of them. So it's just going to touch there. Just going to touch there, either on the top end or on the bottom end. Let's go ahead and find our y-intercept by letting x be 0. Let me erase this. Give me a little room here. Let's find our y-intercept by letting x be 0. Well, -3 squares 9, 4 squares 16. So it looks like this hits at 2 times 9 times 16. I'm not sure what that is. 288. So the y-intercept is 288. Okay. So it hits clear at, so that's the point 0, 288, right? So way up there. What is our degree? Well, if we multiply this out, we'd have 2, and this would be x squared minus 6x plus 9. This would be x squared plus 8x plus 16. Anyways, we keep doing all this, and this ends up being 2x to the 4th plus a bunch of junk. And then we multiply the 2 through, so I'd have 2x to the 4th plus a bunch of junk, right? So the degree is, it's a degree 4. So that means there are at most 4 minus 1, 3 turning points. At most 3 turning points, okay? And then the graph behaves like the power function 2x to the fourth for large values of x. Okay, so let me erase a little bit of this, and then we can kind of sketch out a little bit of what this is telling us information-wise. So let's start with our end behavior. So since it's an even degree, n is even, so think it's kind of like y equals x squared, positive x squared. It's either going to go like that, or if n is even and the leading coefficient is negative, then it would flip that over like negative x squared. Well, in this case, the end behavior says is a positive 2 in front, so it behaves kind of like x squared. So this will go up to the left and up to the right. So I know it's going to touch there. And then at most, 2 turning points. So, well, here's one turning point. It's got to go up here and hit clear up at 0,288. That's way up here, so this is definitely not to scale. So it's got to turn at some point, and then it's got to come back down, hit here, and it'll go back up again. All right, so we kind of know this is kind of what this looks like. Again, I did not graph any points. So to be more accurate, you'd throw some points in. We already know that we have a 0 at -4. So maybe you could throw in a couple to the left, a couple to the right. And you could throw in a couple to the right of the 0 as well as between them. All right, so those are some points you could throw in. We already know 0,288 as well. So again, this is not drawn to scale. That's kind of how you get a feel for it as well. As far as what the graph will look like, let's keep moving on here. So next one. This one we got -2x cubed times x plus 2. Let's go ahead and start with finding our zeros. Here's our equation. 2x cubed, x plus 2. Find the zeros, where are the x-intercepts? So this is like x, 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 and then we got x plus 2, right? So we set each of those factors equals 0. So x equals 0, x equals 0, x equals 0, x plus 2 equals 0. So it looks like we have x equals 0 with multiplicity of 3. There's 3 of those. And then over here, when we subtract 2 on both sides, x equals -2. There's only 1 of those. Multiplicity 1. So x equals 0 with multiplicity 3. So since it's odd, it'll cross through. So it'll cross through either increasing or decreasing on the graph. The next 0 is -2, and there's only 1 of those, so it's going to cross through there at -2, either increasing or decreasing there. Now let's go ahead and find our y-intercept by letting x be 0. So if we let x be 0, 0 times anything is 0. So the y-intercept is 0, which is at the origin. We already knew it hit the origin because the x-intercept is also 0. The degree here, if we were to multiply this out, we would get -2x to the fourth minus 4x cubed. So the degree is 4. It's a fourth degree, which means at most there's 3 turning points. And then it behaves like the power function -2x to the fourth for large values of x. So what does that mean? Well, it's a fourth degree, so n is even. So if the leading coefficient's positive, it's kind of like x squared. It goes up to the left, up to the right. If the degree is even, but the leading coefficient's negative, then it's kind of like -x squared, which goes down to the left, down to the right. Well, this has a leading coefficient that's negative. So or this situation here. It's going to go down to the left and down to the right. Down to the left and down to the right. And so then from this point, we could just plot a few points to kind of get a feel. So it's going to come up, it's going to cross through here, and eventually cross through here as well. But let's plug some points in. Let me erase a little bit so I have a little bit of room here. So I have negative 2x cubed times x plus 2. We're going to plot some points. I know I have an x-intercept at negative 2, so it'd be nice to throw in maybe negative 3. Negative 1, I know 0 is 0, maybe 1 or 2, right, as well. Let's throw in negative 3. So negative 3 to the third, negative 3 plus 2. So I get negative 27 times negative 1. So it looks like I got negative 54. Negative 3 gives me negative 54. So this will shoot down really fast because it's got to hit clear down here. All right, that's negative 54. Then I throw in negative 1. Looks like I get 2. So negative 1 comma 2. So it'll come up. I mean, ideally, I'd probably throw in like negative 1.5. I think that actually hits up here a little bit, and that's going to come down. I might have to throw in negative 0.5. It's going to cross through here. Let me throw in 1. If I throw 1 in, I get negative 2 times 3, 6. Negative 6. So right here, kind of hits here. Anyways, and it keeps going. That's a little bit more accurate of a look. Oops. And of course, I could punch it into the decimal scrapping calculator and just get a little better look at it. But we've got a nice feel by plotting a few points there. Let's do one with some decimals now, and then we'll call it good. So find the zeros, multiplicities, and behavior. So first of all, here's our function. So if we find our zeros, I'll take this first one. It looks like I have 3 of these x's. So x equals 0 with multiplicity of 3. X equals 0, multiplicity of 3. Odd multiplicity is going to cross through. So at 0, it's going to cross through either increasing or decreasing. The next one, I take x minus 1.5, said equals 0. So I have 1.5, but there's 2 of those with multiplicity of 2. So 1.5 multiplicity 2. So it'll just touch it. At 1.5, it's just going to touch it either from the bottom or from the top there. The last one would be negative 1.5 with multiplicity 2. So it's also going to touch right there. Negative 1.5. It's just going to touch right there. So crosses at 0, touches at the other ones. If I throw 0 in for x to find the y-intercept, erase this. 0 in for x. 0 cubed, 0 minus 1.5 squared, 0 plus 1.5. Well, 0 times anything is 0. So the y-intercept is 0. Hits the origin again. The degree, if you were to multiply this whole thing out, you'd have x cubed times the x squared times the other x squared. Well, x 3, 4, 5, 6, 7 x's and a bunch of stuff. All right, so this is x to the 7th. So the degree is 7, so it has at most 6 turning points. And who does it behave like for large powers of x? It behaves like that first term, x to the 7th. So the degree is odd, n is odd. So if the leading coefficient is positive, it's kind of like x cubed. It'll go down to the left, up to the right. Whereas if the degree is odd, but the leading coefficient's negative, it'll flip that over. The x-axis go up to the left, down to the right. Well, in this case, our leading coefficient is 1. It's positive. So we're this scenario. We're down to the left, up to the right. And then it's just a matter of plugging some points in and connecting the lines to get the graph. So this is going to come up. It's going to kind of hit here. It'll come down a little bit, and eventually it's got to kind of work its way back up, cross through here, and then it's going to have to come back down eventually at some point, hit here, and come back up. So if you notice, this one's got 1, 2, 3, 4 turning points. It could have had 6, but again, you can plug in some more values. In fact, we'll take a look at this in Desmos and kind of show you a little nicer look at this by using, instead of just using our concepts to construct this. Y equals, it was x cubed, and then it was x minus 1.5, oops, times x minus 1.5, that was squared, and x plus 1.5, and that was squared as well. You can kind of see a little better look at that one. But anyways, hope that kind of helps. Get you started on 4.2. Thanks for watching and taking notes. See you next time.